recording. So, in the last lecture, we started to look into how function calls work on modern systems, especially on Windows x86. So, now let's continue with that. So, we already learned how simple function calls work. So, with a few arguments, a few more arguments, then how it works if we try to pass a structure or as an argument, or if you want to have a structure as a return value. There we have seen that since those data types doesn't fit into a simple CPU register, they are just passed by address. So instead, the register contains the memory address where the structure resides, respectively, where the structure where there is empty space for the return structure to be written to. And the next thing we will take a look on will be how does it work if we have other data types. So currently we have only handled integer types, although we only handled in this part int structures, although we are in this case of course only handled other integer types like int64 or short or char would work the exact same way. They would use the same registers. When you have more than 4 arguments, it would similarly pass them through the same registers and put them in the same way on the stack. So there is nothing particularly special about how other integer types are handled. However, if we switch to double or floating point, so basically to types which are non-integer that the CPU can natively handle, other registers will be used. So we can set up a test case here. So let's create a new function. Let's say it will return a double. My function d, and let's give it two integer and two double arguments. So we will stick to 4 arguments for now. So this will have 3 and arg4, but we'll make them double. And like with integers of different sizes, with doubles of different sizes, it will not really make a difference whether we have double or float. It will still use the same register. Okay, we don't really need a function to do anything, so we can just keep it as simple as possible. Let's say 1, 2, 3.4 and 5.6. So we have some arguments. We also need a return value. So double my red d capital R. Let's put a breakpoint here. Let's remove the other breakpoint and let's take a look how this works. So as we remember, the arguments are usually prepared in reverse order. So we start preparing the last argument, and last we prepare the first argument. So here it is made quite the same way. So we see here the XMM registers are used instead. Those we can visualize here when we turn them on. So we have wait, that's the right. Is that the right one? Should be the right ones. Yeah, I think. Let's see. So we make step. No, these are not the right ones. These are the right ones. The naming is super cryptical, so it's sometimes easy to forget what one is doing. So now we should see the change. Yeah, and we can also notice that we are using here the registers 2 and 3, while they are actually start at 0. And the reason is that, of course, 0 and 1 would be used for the first 2 arguments, and even if we don't use the first 2 arguments for doubles, but use them, for example, for an integer or for an address, the numbering will be maintained. So you it kind of behaves a bit like a union in the sense that you either use one of the registers, but you then because you didn't use it, not save it to use it later on. The reason here is that you really just want to have the thing as a bit more easy to understand when you read the assembly, a little bit more error proof. So if the order of registers of register usage would change depending on whether other types are passed, that would be a bit more confusing. So it is more elegant in a way to just keep always the same number for an argument at a given position, and not change this at all. So then we of course here we will set our integer registers, and then we go to our function call. And as we see in the function, it copies those four data sets back to the stack. So if we would have a sixth and seventh argument, this would here they would be passed on a stack like with the other function. Then we prepare a few things, and then we just return 0. So we use the XOR operation to return the input value in the XMM0 register. And so once we exit the function, we copy the XMM0 register back to the memory where we wanted to live. One thing that here is a bit different than with the integer use case, we can demonstrate this. Let's make the first argument also a double. Of course, for that we need this to be double as well. Or actually, let's do the float. Why not? And then let's add a few more a few more values here, just for fancies. 3. Wait, that was 5, 4, and 6. Right. So here we want to be correct. So we add an F, indicating that it's a lower precision number. Then we add an integer argument, 7 and 8.9. Okay, let's run it again. So we see here that, as expected, so first of all, we are preparing the few arguments on the stack. So we are copying the data into the registers and then moving them to the stack. So for the last one and the second to last one, we are just putting them on the stack, and the other ones we put as set into the registers here. And we see that we use the same register for the first argument as we use for the return value. And when integer function, when we scroll further up, we remember that there was actually a bit different, because there we use different registers for arguments and a different register for the return value. So if this would be fully analogous, then the return argument would be not EAX but ECX. But no, here in the x86 calling convention, a different argument is used for the return value, which in some ways is nice, but in other ways, of course, it is more complicated. So here for the doubles, they just selected to use the same register for both functions. And interestingly, if you would look on some ARM64 disassembly with function calls, there the same mechanism is used. The first argument is used, the same register is used for the first argument as is then used for the return value. So in this way, the usage of a dedicated return register, different than an argument register, is something x86 typical, and not commonly reproduced over other architectures. Not even in the x86 CPU architecture, this wasn't maintained for the floating point numbers which have been added later. So just on a short tangent, very extremely old CPUs from the last millennium, they did not have a floating point unit, so they only did integer math, and the ability to handle floating point numbers was added as a additional chip that you had to plug into a mainboard at the very beginning. Later, of course, this functionality was integrated into the standard function set, but the way internally, of course, this was used remained the same, since people wanted to maintain software compatibility as functions and features get integrated. Okay, so I did much to this double functions. So let's take a look on yet another interesting mechanism with regard to function calls. Sometimes, well, normally you know how many arguments you want to pass to your function, but sometimes you might find yourself in a situation where you would like to create a function which does not have a fixed amount of arguments. And this, in fact, is possible in C and C++. It's called a variable argument function, and it's defined like this. So we first need some return value. We could use void, but let's just use int. My function for variable, and let's give it some arguments that we actually define. So let's start with an int and args and comma, and then the rest of the arguments we don't know, so we just write 3 dots, and of course a function gets the function body. So we can have a arbitrary amount of defined arguments, and then we can, as the rest of the arguments, use the triple dot function. Semantically, I guess you could create a function which only has variable arguments, but that would practically put you in front of a few practical challenges how to access those arguments. So this is something that is not practiced. So at least use, for example, in this case, an args would be a place in, for example, number of arguments, but it could be for anything. You could also have like just a dummy argument, just that there is one. There are once a bit later we will be taking a look into actually doing more interesting things with strings. There are functions which which are made like this, but instead of a number of arguments, they take a format string, and then you can provide additional arguments. So before we can use this variable argument function, we need to add an additional include, which is not part of the standard includes. Std h is the header's name, and this gives us a few macros which will allow us to access those not defined arguments. So first we define a type which will represent our list, a va list. Va is just short for variable argument. ap argument pointer. Then we need to somehow populate it, and there is a macro va start which writes to ap, and it takes the address of the argument which immediately precedes actually it just takes a name which directly precedes the variable argument list, and we then later can take a look inside what happens. So this is quite complicatedly defined, but at some point, if we dig deep enough, here it's just declared our start ap and x. In principle, we could construct this manually. I see in this version of Visual Studio we don't really get to see what it does internally, because it just goes into yet another function call, which we here don't have. But we could dig up it at the sources, or we could construct it manually. But let's first continue here with this thing. So we have our list, and we have the count of arguments. So let's make the function do something. For example, let's just sum up all the arguments that we have and return the sum of all of them. That would be simple enough. So int sum is 0, since we haven't done anything, and return 0 sum. Then we need the loop idea. So for int e by 0 is less than n count, since this is our argument count, and of course I++, so that we increment our that needs to be a semicolon. Check. And now we will need to take the value, so int val, and there is again a macro va arg ap comma int. So we specify sorry, just ap. So we specify our argument list, and we specify what type we want. The thing will internally go through it, and then we get our int value, so we just write sum plus equals value. You can take a look on the definition. So we have the list and the type, and it in principle just steps through the whole thing through the pointer. And once we are done, the standard says that we should finish with VA and AP. But as we see, this really is not really necessary. It's just assigning 0 to our VA list, and this thing is just defined as a type of char pointer, at least in this configuration. Okay, let's make it a bit prettier. This can be here. Okay, and then let's use the function. So let's be lazy, just grab this one. And we have 10 arguments, so we write 10, comma. And as you can see here, we need to know which type the argument will be of. So this is a little bit complicated. And in this case, we have made a function which just handles integers. We could make it to only handle int 64s or only handle doubles. Or if we would provide some more information to the function, something that describes the list of arguments that we are passing to it, we could of course use any sort of arguments there. We can use this VA to retrieve any argument, and we could also be a bit smart about what we do and access them by index, although this mode of access is not something that is intended. So this macros that we have included that we are using are really just designed for sequential access of the arguments. I guess the by the book solution would be to create an own list, populate the list or an array with the arguments, and then access them by index. But as we will see, the way this actually works under the hood, it would also allow us quite easily to access those things by address. So let's run it. And as we can see here, and compare it to before, everything is just shifted, and we have the counter first inserted first here. So the way the function is called is in no way different from how any other function with a large amount of arguments would be called. So let's just step into it, and we can also remember that when we do this putting of additional arguments onto the stack, that we leave some room, and we have seen before, that we will now see again, that the functions are, first thing usually they do is to copy the arguments which they have received explicitly back to the stack where they would be if where they could be, where there is empty room left for them. And as mentioned in a debug build, the functions will always do it. In a release build, this space, they will not do it unless they need to. And they in fact only need to do it if it's a variable argument function. So there are technically two reasons why this small amount of space, basically for keywords, has been left on the stack. The first reason is because they wanted this variable argument functions to work in a simple enough way, so that if you copy those things back, what you basically get in memory are all the arguments laid out in order, in reverse order, but still ordered. And for other functions which are not variable argument functions, the space being there might be used as a temporary scratch space. So normally the functions we use, as you might remember from the last lecture, they are modifying the stack pointer and maybe the base pointer depending on the compiler settings. They will be saving some registers, etc, etc. So they will do quite a few operations just on function entry, on function exit. But if the function is very simple and the compiler is set to release build so that it tries to optimize, if the operation is really simple and even if it needs some temporary memory, this small amount reserved at the before the return address can then be used for it. So the function would keep the arguments that are passed to it in the registers, do some calculation, store some temporary value in that memory, and then return the return value. So this way, very small leaf functions can be optimized. And the term a leaf function means that the function never calls any other functions. It just does everything internally. There is no further branching. So such functions can be optimized quite a lot in this x86 calling convention. So let's continue here. So we put those four things back into memory. We can go there. So it was RSP plus x20. Was it last argument? Sorry, it's copying the wrong order. So let's go RSP plus 8. RSP plus 8. Yeah, now it's correct. So we have first argument is our count A. Then we have some garbage which just is there. So all the arguments on the stack are always 64-bit on a 64-bit system. And then we have our 1, 2, 3, 4, 5, and some garbage 6. So there is some garbage because the compiler, when it created the instructions to call to put things on stack, used this dword operation, which tells the CPU that it only should handle 32 bits, so 4 bytes. And in this case, it will only set those values and clear those 4 bytes. It will not touch the other 32 bytes on the stack. There just remains whatever was there before. So there is some garbage. So let's continue. Then we have somewhere wait, where were we? 6, 7. Where's the 8? The 8 is here. 9, and we had that again at 10. So as you see, everything there is laid out quite nicely. And in principle, when we go to the AMINET window, we can write some simple thingies. RSP plus 8. And if we say this is a int64 for asterisk, and then we take 0, that is not quite right. We get, as said, we get some garbage, and then we get a thing. So we could also then tell it is just a integer, and voila, we get the right values. And then we can just go through an array. So effectively, it really is just a normal array, as we have learned in our lecture about pointers and arrays. This is just an array which can be in order stepped through with an index, and every argument passed to the function can be accessed. If it's 10 arguments, 100 or 1000 arguments, it doesn't matter. This way they all are laid out in memory, and you can access any of them whenever you need them. So of course, here we have access this RSP register. There would be a more C plus C-like way of doing it. We can just here get the address of our first argument. Wait, why doesn't this work? Because it might have not yet been here fully prepared. Let's just step a little further. So when we are using the arguments by name, we of course need to ensure that we are in a place in the code where this thing here will understand what this is. And again, 1, 2, and so on. So basically, this trick is what this start function does. It saves such a pointer into our VA. So when we look here on VA, this thing, you can take its address. I mean, it contains an address, so void asterisk is just the address it should have. And then if we go for the address of this thing, Wait, why doesn't this work? So you can see the definition of the VA. This is just char asterisk. We have not set it yet. That's why it contains garbage. We need to set it, of course. So void AP, and then the other thing. Yeah, alright. That of course is off by 8 because this thing would be like one too little, because that would then point to this first argument, but AP is of course made to point to the first argument from the list, so it is advanced by 1. So if we here just add plus 8, we get okay, we cannot add something to avoid, we would need to cast this. Can do like this, plus 8, and then we get the same value. So basically this AP is just a pointer to the first entry in our argument array, and this VA arg will just take the value and then advance the thing by 8 so that it points to the next value, and then we repeat that until we are done. And we are supposed to use this end function so that we clear it, that if for some reason we would later try to call V8 again, or some other thing that is not valid, that we would get a nice defined crash. There is a question. Okay, so there is a question in the chat. What does it mean to put a value on the stack? So let's go back to a simpler example. Let's see which one would be good. I just go to the function call. Actually, we can just start with this function call all over again. So the stack is a portion of memory that is allocated for every thread that runs on a system, and this memory is used for all the immediate needs of the functions and the function call tree on that is being run by the thread. The stack memory is pointed to by the stack pointer register, RSP, and this register has a special functionality. So it's not a general purpose register. It is really designed to contain only memory addresses and work on those memory addresses. And when we clear all of this, so we have a stack pointer that points to somewhere. We can take a look there. Oops, we just want RSP without anything. And we move a little bit around, and then so once we have this memory address, we can write data to this stack memory, and writing some data to this memory pointed by the stack pointer means to put something on the stack. There is the meaning is not necessarily always referring to exactly the same operation. So in this case here we are writing to the stack, but we are not changing the stack pointer. In other ways of using the stack, when we put something on the stack, we might also mean that we write something to the stack and then advance the pointer to the next free region in memory. And when you write assembly code by hand, this is something that is more often used. But of course this means that you have the operation of doing something and then the operation of updating that pointer. And since the x86 instruction set is a complex instruction set, operations can contain an additional offset like here. So there really is no need to break it up into multiple instructions. Instead, what you can do is you can just advance the stack pointer by, let's say, 10 or 20 bytes or however many you need, and then you just put the things in there using the pointer plus some offset, be that positive or negative. And a thing that is also important to note with regard to how the stack address layout is handled. Normally, with normal memory, you start at some address and then go to higher values. With the stack, it is customary to implement everything the opposite way. So you start at some address, and when you add data to the stack, you are going towards lower addresses, not higher addresses. This is quite convenient, because then if you advance the stack to some position, you can just use plus to access valid offsets, while if you would grow the stack the normal way towards larger registers, then you would always need to use minus values. And positive values are nicer because they don't contain so like a negative value, you always need to check to think about um, it's whether it's signed and so on, and you always have leading ones, so um, it just looks nicer and is less error prone if you use positive offsets. So that's one of the reasons why the stack was designed this way in for most systems. Of course, in some very exotic systems you might find different implementations, but in fact the direction the stack grows is defined by the hardware, since you have also operations which put a value onto the stack and automatically advance the stack pointer. So we will be able to take a look on such an operation in a second. We just click through here again, and when we go here to our function at the beginning, we also want to view the registers. So putting the registers back into this reserved scratch space, of course, is done without changing the stack pointer. We just know where it is, and we use the right offsets to access it. So basically you can kind of even see it here in the instruction that 0, 8, 10, 18, 20. So the numbers, the offset numbers are really just partially encoded inside the instruction. Okay, so let's just step through that. And then we have here this push instruction. What push does is it takes some register, in this case the base pointer register. It puts it onto the stack, so it copies it onto the stack to the location the stack points to right now, and it advances the stack pointer to the next location that is available. So when we move the memory thingy here, so that you can see both, here we watch the registers, stack ASP, then here in this line we have our stack pointer. When we execute this push operation, okay, in this case we don't see apparently a change because there was the same value already in it, but we see that here the stack register has been changed. We could try to rerun it so that we visualize this correctly. Let's see again, step, step, step. Go again to ASP, and we can just zero out everything. That can we? Yeah. Wait, doesn't this work? ASP. Doesn't allow us to edit. Okay, we could only edit on the other side. It shouldn't usually not be read only. Let's just write here some. No, it doesn't allow us to edit this. Why? And now it works. Guess the new Visual Studio version is a little bit bugged. It does not. So we just put F's everywhere, and then when we execute the push, we will see which place here was overwritten. And we can also write down the value just so that we don't forget it. Memory, okay, push, step, and voila, the content of the RBP register here, so a lot of zeros, DCB, and it ends with CC0. So we have it here. Of course, we notice that it has the little endian notation, so the least significant bits FCC0 are actually here at the very beginning, C0, FC, and so on, and zeros. And then when we switch to our immediate view, RSP, we see that RSP has been advanced by 8 bytes, but it has been advanced towards RSP towards smaller addresses. So instead of going here to what would be the next one, 60, it went back to 5-0. So it's kind of being advanced uh, the opposite way that normally you are advancing arrays. And since this push works this way, and also as we have said earlier, the stack is used for return addresses for by the call and return instructions. The direction the stack is operated in is in fact hardware defined, unlike many other things about calling conventions. So as you might remember, which registers are used and which registers are volatile and which are non-volatile is pretty much up to the people that write the compilers and that make the standards. The hardware at this level doesn't care as long as you are using compatible general purpose registers. But with regard to the stack and how the stack is handled, this is hardware defined and you do not have the liberty to change this. I guess of course you could try by hand to use multiple instructions to emulate a behavior where the stack grows into the other direction and so on. But this would be just bad practice and there is no good reason to do it. So one can do it just for fun, but not in practical use. Okay, so I think this should be detailed enough about how the stack operates and what putting something on the stack means. Just one more complementary thing. There is also the opposite process of taking something off the stack again. And this is done. Well, of course, you can just read and write to any location in the stack using the move operation, but the reverse operation to a push is the pop, which is used here, which really does the opposite. It changes the stack pointer, and but this time it advances it towards more positive values, and it takes the value it was pointing to and writes it to the register. So if you want to save all the registers and restore all the registers, you would just make a list of pop and push and pop instructions, push at the beginning, pop at the end. And in fact, if you want to save all the registers, there is I think also an instruction that we just is like many pushes, and later another instruction this is like that is like many pops in the right order, which then just does this internally so that you can use a little bit less code. Although it's not very commonly used, since it also saves the stack pointer. The stack pointer it cannot save. The base pointer. And no, it also saves the stack pointer. And in theory it is fine because it then kind of changes it in a way that should not make effectively a change. But generally because of this behavior it's not used so commonly. Usually you will just see a manual usage of push and pop individually. And of course when you want to use some XMM registers for floating point numbers, those you might if you need to use the non-volatile ones, those you would also need to push or pop from the stack. But in this case I think we don't do that anywhere. No, we don't. So the first few registers out of the quite many 16 registers that are used for floating point numbers, they are also defined as volatile, so you are free to change them inside of your function. You don't need to restore them later on. Okay, so let's continue here. So we had how far were we? Let's see. I think we were past the start, right? And then we have this VA, which, as already mentioned, operates just like getting a value from. So in principle, if you want to be as exact as we can, this VA instruction would be something like int64 asterisk ap plus plus stern. So it basically it takes the value where it was pointing to and it returns the next and it increments the thing using pointer arithmetics to the next entry that we haven't yet received. And if we look here, it is much more convoluted, but in the end this will more or less be exactly what is happening here. There is as you see here some internal checks whether the size is bigger than that than the integer 64, which the platform can natively handle. And if it would be bigger, then what it does is it does not return to you just the register value, but it knows that that this position would contain not the actual value, but only a pointer to the value, and then it would accordingly handle the situation such that it would return to you the pointer in a way that then your code would create a copy operation and copy the value. So our manual stand-in here only would work on standard types. It would fail if you would want to pass also a structure as a variable argument, which brings us of course to the point that yes, you can also pass structures here or other objects as arguments. You just need to know how to handle them. Anyhow, so our function will run. We can put a breakpoint at the very end. This crashed. Why? Did we press this? No, we didn't press it. Did we provide too many arguments? 10. We have 10 arguments. It should be fine. Let's run it again without doing anything. Yeah. So the reason it crashed is probably we typed here something, or actually I think I overwrote some memory here with all F's. That's why it crashed. So if we just run it without screwing it up first, it just correctly arrives at the return value, which I guess 55 will be true. It looks plausible. And then of course it returns it, as we always know, through the AX register. So that much to this variable argument functions. And if you are using C++ and not just C, there is another nice thing you can do with regard to a function and function arguments. Let's just copy some very simple function from here. So sometimes you might find yourself in a situation where you want to specify some additional argument, but you know that in the most cases it will always be the same value, and then you think, yeah, I don't want to type every time this additional argument, especially if it might be a more exotic value, like, I don't know, 1, 2, 3. And you need to remember that it should always be 1, 2, 3. And as you have seen here, we can just write the value we want directly in the argument definition. And then if we try to call this function, let's do this twice. My ret1 is equals 1, 2. And then we can have a special case where we actually want to specify this argument, fast4, 5, 6 or whatever. And the compiler is perfectly happy with it. So, but they only specify 2 or 3 arguments. Of course, we could have more. We could also add here a I don't know, 789 argument. Of course, the name needs to change. And the compiler is in any situation happy. The only thing you cannot do, which some other languages would allow you, you might want to not specify the third argument, but specify the fourth argument. So do something like this. And this doesn't work. So you cannot leave this empty. If you want to specify the later argument, you need to specify the right value for the before argument. I think on Visual Basic, in fact, you could really just have a function with a lot of commas and then write to the right address, and here it would still fill in the right values for you. But C doesn't do that. Be that good or bad depends on the point of view. Generally, if the language allows you too much implicit things to be done, this is more error prone. So NC tries to rather fail than to allow you to make an error that, while is an error, will not be detected instantly. So let's put 2 breakpoints and see how this is implemented. And but we don't need this breakpoint anymore. And as we see here, both calls look exactly the same, and in fact both calls look like any normal function call. We just have our registers and values are written to them, and here the compiler just looks up in the definition which value to put, and this value is actually really put here. So there is no difference between specifying those arguments manually or not. For the final version, final resulting code, it is just a convenient shortcut for the developer that you can have those default arguments and you don't need to provide them. And of course, when one thinks about it, this is like one way of doing it. And the other way could be, for example, that you make like a dummy function which only takes 2 arguments and then fills in the other ones. And then the trade-off basically is that you have more function calls while you have less code. So you have more function calls but less code, or you can have this version here where you will have more code because you always write those arguments even if they are not specified by the developer, but then instead you have less function calls. So in principle, there are, as I said, 2 ways this mechanism could have been realized. Generally, however, it's always realized this way. The reason for this is simply that usually you try to avoid making unnecessary function calls, since this is usually related to quite a few operations. Even if you of course would then try to optimize this, as I mentioned before, you can really nicely only optimize short leaf functions, and such a intermediate function would not be a leaf function. So usually there would be no benefit, and memory nowadays is still cheaper than the compute, so it's better to just have a slightly larger program and save on one function call. Okay, so that much to those functions. Now, since we have already touched on C++ and functions, there is yet another nice thing that you can do with C++ that is related to functions. That is, you can create so-called function templates. But before we go to this, are there any questions? No questions? Okay. Good. So if there are no questions, then let's continue with function templates. So the idea of function templates is a bit similar to this automatic arguments, that you kind of want the compiler to fill in things for you. It is just significantly more elaborate, because here it's really like just look up one thing and enter it. The function as such just remains a normal fine working function. With templates, the idea is that instead of not knowing a value of a default value of an argument, that with templates you want to not know, or rather not define the type of an argument, so that you, for example, create a function which can take any type, at least within certain reasonable, let's say, limitations. On a practical level, of course, if you make a function that always computes the sum of all the arguments, and you would use it to pass a type for which the plus operation is not defined, then of course that thing will then not compile. But here, for example, you can create a function that will take doubles or integers or other sized integer types, and always return a sum of the provided arguments in the same type that we had before. So we first write template, a type name, and then some placeholder, and we could specify multiple types, so type name T, type name U, for example, but we could of course define a default type. So we have here 2 types. One will be, the U will be the return type, T will be the input type, and by default they are the same, but we could make them different. So IU my sum, and let's say that it will have 10 arguments. Oops. Yeah. And now, of course, instead of providing the type, we just write T everywhere. and then we just return or u at is equals 1 my plus 2 3 4 5 6 7 8 9 10 1 2 3 4 5 6 7 8 9 10 and then we return. Okay, now let's use it. So my right one is equals sum. So for this we already have some test values, and then let's do the same thing for double. My at d point null. Oops. Okay. So we now call the same function with different arguments, and let's see how this is implemented. And just already to tell you how it works is the compiler will just see that we are using a certain type, and that there is a template, and then it will basically take this code, replace the t and the u with the right types, and then compile it. So basically, while we have this function in our code only once, in the compiled code there will be 2 copies of this function implemented with different types. So this is the mechanism how this works under the hood. Right, I already defined that. So we have here our call, and when we show names, then it will always say my sum, and here my sum. But you see already that it adds in this pointy brackets the types that it filled in, and generally when debugging every function needs to be addressable by a unique name, and this is how these template names are created. So you have the actual name plus the template argument list, and this defines your function name within the program under the hood, so to say. And here, as you see, the ways those arguments are filled is correct to the respective type. So here in our integer version, we use the integer registers. Here in our double version, we use the XMM registers. And then if we also take a look here, it shows us still the address, and we see that while it's in our code the same function, in the machine code, in the compiled machine code, these are in fact 2 completely different addresses, since 2 completely independent instances of this function have been created. So this one version, which operates here just with the integers, and then if we return from this and then go to the next one, we will see we will arrive in a different place where we have completely different code using different registers and different opcodes. So as you see, the mechanism behind this is quite trivial, but this template system is extremely powerful. And when we continue with more C++, we will see that this template mechanisms can also be applied to structures and to classes and everything else. So here, since we were on functions, we'll only take a look on this one use case, but there will be a separate lecture just all about templates later on during the course. Okay, so I think with regard to the functions and their reasonable usages, I think I have shown you all there is. So in this case, then let's do something unreasonable. No, there is one more thing I could show you, which is probably useful before we continue with the unreasonable things. That is, let's just grab a function again. So function pointers. So if, as you know, everything that lives in memory can be addressed by a pointer, and in fact, a function, since it lives also in our memory, can also be addressed by a pointer. And let's make an example. My func cb. So we have a standard function, and then we want to pass to it as an argument the address of another function, which this function then will be using as part of its execution. This is a mechanism that is very popular in C programming, because in C you cannot easily attach functions to objects. Uh, you can only do it through function pointers, and often you might want to implement some function that does something with your input data, but then the final step or an in-between step somehow customized, so that you don't need like to write 2 or 3 versions of the same function with only very small internal differences. So you can outsource this internal thing into 3 helper functions, which you then can pass to your actual function. A real world example would be, for example, sorting functions. So you might want to sort an array, and then you want to define what means that element A is greater than element B. And for this, for example, such a sorting function would then take a pointer to your array, the size of the array, and it would take a pointer to a function which then defines the size of, then defines the comparison which is greater and which is smaller between 2 elements that it is fed to. And of course, depending on many other implementation aspects, such a sorting function and the level of abstraction might need other helpers. So for example, to swap 2 elements, you might want to use a helper function, etc. But here we will just use some function that does something. So actually we could, for example, take already the function we have here, this one. So we only need to properly define the pointer to it. So the way you define a function pointer is like this. So you have the return type of the function, then you open brackets, you provide an asterisk, then you provide the name with which inside your code the thing will be addressable, and then you have just a normal argument list that the function wants to consume. And in principle you don't need the names at all, because this is just the pointer, so you won't be referring to those things anyways. You just need them to be consistent. So in this case, let's just do it like this. So the function pointer, unlike any normal pointer, does not need like an asterisk to be dereferenced, because kind of there is nothing to dereference. If you would dereference the function pointer, you would just get the machine code of the function, which would not be of use to you usually. It might be in certain scenarios, but usually it's not. And if you have a function pointer, just by providing the brackets, it is clear enough for the compiler that you intend to call it, in which case it will correctly here just implement a function call. So let's try this. So let's grab our sample from here, then grab the name, zack, comma, zack. And likewise, when you have a function, then you don't need to provide the dereference operator, this address operator normally. There are scenarios when you have classes and you want to access a abstract address. So basically, I get the offset of a function inside of a class without having the actual object instantiated. Then you would do it with this AND operator. But in just C, you don't. You just have here this function name. So let's just see how this works. Zack. So we are here. We have our 3 registers, ECX with, let's remove the names again. So we have our ECX where we save variable 1, EDX where we save variable 2. As you might remember, they live at RBP and RBP plus 4. And then we have an instruction called load address. We can use it instead of move to fill in here the address. Let's see, do we see something more interesting if we turn it on? No, it just has the function. The reason why we are using a load address instead of move to populate the R8 register is that if we would have here a better disassembler, I would probably see that what we are generating is an address relative to our current position or something like that. It is not usually typical to use full absolute addresses. The reason for that is that an absolute address would be quite inconvenient, because then your application would always need to be mapped into the exact same memory range, and there are various security measures which nowadays, like address space layout randomization, which actively try to avoid it. So modern code tries whenever possible to use relative addressing. And just on a note, how the system handles applications which are older, which require a fixed address. So this is simply done by reading the program and then changing all the fixed addresses to their new location once the thing was remapped. And of course, since disassembling everything would be very unpractical, the PE file format that Windows uses for access and DLLs and other executable files is made such that it contains a list of all the locations which contain absolute addresses. So so the process of correcting the addresses once the executable is mapped into memory is quite trivial. You first just map the whole thing into some location. If it's the location the object, the image wants to be in, then you are already done. If this is some other location, which for some reasons might happen. So with an executable, it is not very likely, because the executable is usually one of the very first things that are mapped, except for the NTDLL and so on. So it can pretty much get to reside wherever it wants to. But as soon as the executable starts loading DLLs, you might load two DLLs which both their respective developers wanted them to reside at randomly the same address. So that would be, of course, a conflict. So one of them needs to be relocated. This is why the PE format, even from the very old days, from the last century, have already been designed with the ability to do this remapping. And the way this works is then that after you mapped it to this non-expected location, you see that you just consult this list of hard-coded addresses, and then what you basically need to do is you know where it wanted to be, you know where you put it, so you can calculate an absolute offset, sorry, a relative offset from that, and then you have this pointers which point you to addresses which are written inside of your image, and then you just take the value, add your offset to it, and write the value back into memory, and voila, you end up with the whole image being successfully relocated without having to disassemble a lot of code. But of course, since this operation still, especially for a very large image, might still take hundreds or even thousands of instructions, you need in the end to read and write a lot of memory. It is typical that modern compilers will just try to use relative addressing, in which case you don't run into this necessity to change those things. So that's that. So let's continue here. So we just use so for a function we just use the normal, in this case R8 register. If it would be earlier, then it would be RDX. If it would be much later, it would just write the address on the stack. So here the pointer is like any other integer type. It doesn't have anything special about it. And then if we see here, when we want to call our thing, we save the address into RAX. Do we wait? We should call it what? No, we don't. This RBP plus 80 is some other value. Okay, so this will be it. We just put it to Rx, then we from Rx put it here. That is kind of unnecessary. We just copy it into another location, but okay. Then we just prepared, in this case, only the two registers, since our function only takes two registers, ECX and EDX. And then we can call and specify to the call the memory location where we wrote the thing to. There are call opcodes which directly take a register. So if you would write this code here manually, you would just load the address to rex, and then you would just here call rex directly. You would not waste time on putting it back into memory and then using a call which then has to read memory back again. So this is quite inefficient. But as you see, it's not really in any fundamental way different than from how a normal non-by-pointer function call operates. And then of course here the function returns, at which point it doesn't really care about just a normal return. It works the same way, whether it's invoked by called by pointer, or whether it's called just normally from the code. Okay, so any questions? Okay. So since there are no questions, then let's continue with doing a few unreasonable things with functions. So as you might remember, um, whenever you are returning from a function, the return opcode is reading the return address from the stack, removing one entry from the stack, and then jumping to this return address that was located on the stack. And from this we can already deduce that if we just access the stack memory directly, we could put some other function on the stack, and then if the return instruction hits, what would happen is that we would in fact jump to this other location. We would not return from where we came, we would return somewhere else. So obviously this sounds kind of error prone, and normally you would not do such things in your code, but this mechanism is in fact how one of the most common nowadays ways of creating exploit code, so-called return-oriented programming, actually works. You're writing some addresses on the stack, and then you will end up with a mechanism that will just jump from one function to another, to another. Usually, of course, not to the whole function, but just to the last few bytes of a function, and each of those operations will do something. And after the chaining enough of such short gadgets together, you will end up with some code that will do actually something meaningful. Of course, this is not something that people would do by hand. This is just something that you invent as a concept, and then you write yourself some tool that will, inside of your target process, target image, look for the suitable gadgets. So ideally, you would have something that where you can write a piece of C code, and your custom ROP compiler would then investigate a victim process and then generate for you the correct exploit code that then functionally represents what you written in for example C, but is not made up of normal instructions, but is only made up of addresses within your target process that then will be chained together once you find a way to get those things written to the stack in some victim process. And writing those things to the stack, we have already seen how such things can be achieved in the lecture about pointers. Usually when you write to some array and the array is too small and you are allowed to write more than the array can hold, then you are starting overwriting things on the stack with your stuff, and that's how all those nasty things happen. Here we will really just demonstrate the most basic mechanism without actually going into actually doing anything that could be considered weaponized. So it's really purely academical. So let's create some function. My function 0. It doesn't need any arguments, and we will just call it further down. My head1. This equals, we call our function. We put a breakpoint here. Okay, so we have our function. Right, so now let's prepare some memory. A is 1, B and C, B and C, 2 and 3. Int my head is equals my function 1, which we don't have yet. We return this, so we need to construct a few things. So my function 1 also won't have a return value. but this will be the function that will do the funny things. So void asterisk. That's, as you remember, a universal pointer, ret ptr, which will contain our return ptr, and there is a built-in function uh, address of return address. This is not like a real C function, it is kind of a placeholder for the compiler, that it tells the compiler to look up the return address on the stack. It will be here in place replaced with a couple assembly instructions. It will not be a call to somewhere else. Oh, which by the way brings me to a thing which I in fact forgot to show you. If you add or false inline before a function, then you are in principle instructing the compiler to not do a function call, but actually just take the code and copy it in place where the function would be called from. Although the compilers tend to sometimes ignore those instructions. So plus it does not really is related to how function calls work, so it's not something we really need to take a look at. And nowadays this is a rather small optimization, so it's not something that you would nowadays find in typical code unless you are doing something particularly special like here. Okay, so we get the address of our return instruction. Then we will need some global variable int 64 original return with the original return address. So we don't want in this demonstration to break anything, so we want in the end to be able to fix everything. Right here. So we have here original return address, which is then int 64 asterisk ret ptr. So we know the address will be 64 bits, so we handle it as a 64-bit integer. And now what we'll do is we will write another address to it. So int 64 reference, we will make a function too. Actually don't necessarily need that function too. So we take the address of the function, cast it to a 64-bit integer. I mean, it's already a 64-bit integer, but we just tell the compiler that this is what we want to do. If we would not have this, it would be just incompatible types. So we just tell it it's fine, and then we will return. Let's say we want to return 1, and then we go to our function 2, where we again get the return address now of function 2, and then we want from this to return directly to our original return address. Okay, and let's make this return 0 and the other one will return 1. Let's put like this. So yeah, that is it. So normally, of course, if you wouldn't mess with the return addresses, the way the control flow would be like you call function 0 calls function 1 calls function 2, and then when function 2 returns, the control goes back to function 0, which then returns, giving control back to function 0, and when the function 0 then returns, it gives control back to the calling function. What will happen here is different. We will enter function 0 will enter function 1. Function 1 is not calling anything, it's just messing with addresses. We'll do the return, but instead of returning to function 0, we will end up in function 2, and then when function 2 returns, we will end up in function 0. So instead of like a chain where you are going somewhere and then going back the same way, like any function call normally operates, you are going somewhere for a branching structure of possible function calls, and then you are always taking the exact same way back. Here we will go somewhere and then we will disappear there and then come back from a complete different spot. So let's try it out. Yeah, so we are here, we enter our function 0. We have some memory. Then we enter here our function 1. Function 1 prepares the stack. Since it doesn't have any arguments, it does not do anything with copying anything back or so on. Then we arrive here at our special intrinsic compiler function. As you see, this is not a function call, it is just a load address from RBP plus hex 58, which will be the position where the return address currently resides. And then this value is just written to memory. So this it's written to memory to our red pointer, which is the address of currently just base pointer. So let's do it. Click, click. Now, since we have the address where the return address resides, we can grab the value from there and move it into our global variable, so our original return address. So let's do this. Now we will be overwriting the return address. So we are here using layer to get the address of our function 2. If we show the names, then again we see it's function 2. Maybe I should just leave this enabled for now. Right, so we copy this then here into the location of the return address, and then we return 0, or at least we try to return 0. We restore the stack, some more, and now we execute the return instruction. And when we look on the call stack, we should be returning the call stack is already broken. It's already showing that we will return to function 2. Before we have done this, actually let's redo this, so we see that this really does what I say it does. Okay, right. So now we haven't yet hacked anything. So we see that here the call stack, we start in the DLL, then the kernel for to DLL, then our main, then not our main, the main in a main in our program, but not one we wrote ourselves, one that was is part of the framework. Then there's some more variations of main, yet another version of main, and finally our actual main function. And then we have our function 0 and function 1. But as soon as we here are done with our move operation, the whole stuff here breaks, and we're actually supposed to return to a function we never were in yet, to function 2. And thus we will do so. So if we do the return, zack, we will end up in function 2 without having it called. Now this of course is a bit let's say problematic, because we have not prepared the arguments. So if we would want to actually be able to pass arguments to function 2, we would need to do some more memory preparation and stuff like that. Generally how this behaves is that if you do this, you will get the stack space with the arguments that function 1 has that function 0 has prepared for function 1. Although the stack might, some portion of it might be overwritten already, especially this lower 4 values that can be used as a scratch space. You will not get values that are passed in registers, so there are some limitations to this trickery here. But let's continue here. So in the function, we just normally again prepare the stack again. Then we get again the pointer. And then we override the pointer with the original pointer, so the one that tells us to return to function 0. So here still we have this broken stack trace, and as soon as we do this, the stack trace remains correct, returns to being correct, I mean, and we see that now from function 2 we go directly to function 0 as if function 1 would have never been called. So then we can of course set our return value to 1. So in fact the return value that function 1 set, being 0, will be ignored, which is fine. Then we restore the stack some more, and then we do the return, and voila, we have completely skipped around function 1 and are now directly in function 0. And then the returned value will be of course saved to memory, then returned again, and then here once we are done with everything, we can see that we have in fact returned 1, and this return here was completely suppressed, didn't do anything. Good. Yeah. So that's that. Any questions? Okay. So if there are no questions, then let's think of some homework. Something of course much simpler than this address trickery. Let's just so today is the 23. Write a variable argument function which takes a specified amount of arguments and then computes the mean value of all of the arguments and returns it. That is a very simple assignment. More complex assignment will come later and optional. With that function as a template so that you can specify so that you can use it with different depends like in 64 and float. Okay. Yeah. So there are of course much more things about template functions that I could show you, but as said, we will be having a session about templates and templates only later once we have arrived in the C++ part, where we will be looking into classes and inheritance and stuff like that. So we don't need to care for those things yet. So let's continue. The next thing to show you, if I recall correctly, I think that will be the last thing that will be just C. Past that point, we'll be doing C++, is the basics of memory management. So as you have already seen, there is this thing called the stack, but it is quite restricted with regard to how memory can be allocated there. So we'll create a new project and take a look into other ways of using memory. And let's wait for the project to be created. Let's remove what we don't need. Let's include H. Oops. Okay, so until now, all the memory that you have accessed in the code that we have examined here was on the stack, but you might want to allocate some larger amount of memory. So the stack, I think I mentioned that already in the last lecture, the size of the stack is something that is limited to a couple megabytes or a couple 100 megabytes at most. And when you're creating a thread, you need to actually specify well, either you have to specify, or you just pass 0, which means for the operating system just pick what you think is right. But you can specify this the amount of stack that the function, well, that the thread will have available for its functions. And oh, by the way, that may be one thing I should show you is what happens if you run out of stack space. So we have here functions which call functions, but what we of course could create is a function which just calls itself ad infinitum. And obviously you would not write such a thing intentionally, but you might write something that needs to call itself a couple times. For example, if you make a function which you give it a folder, and it's supposed to, let's say, write to the screen the size of all files in the folder. And you want this function to, if it encounters a folder, do the same for all the files in that subfolder. So basically the function would check, is the thing I just enumerated a file? If yes, print the size to the screen. If no, else case, call I call myself again, but with the subfolder as the path, and then the thing gets repeated. And if you would create a terribly deep subfolder structure, and your function would be significantly more complex, so that it really consumes significant amounts of stack space, then you might end up at some point in running out of this space. And such errors are usually quite painful to catch, but we can just create such a on-purpose demonstration function that just demonstrates it. So let's put it here and let's run it, and it runs until it crashes. So bam, unhandled exception, stack overflow. And as you see in the call stack, we have the function calling itself, and at some point it can no longer show even here. So you might end up in a situation where you cannot even say where you came from into this error situation. And of course, what we could, for example, also do is we could add a global variable. To just count how often we can call ourselves before we crash. Zack. And if we really don't do anything else, we could call ourselves, let's disable hex view, 96 times. That's a lot, but as soon as the function here would get actually something to do, then this number, then it will start consuming more stack space. And then we'll be able to call ourselves less and less times. So if we only add just a little bit of math, we are already dropped to only being able to call ourselves 7,000 times. And of course, the more we do here, so for example, we could, I don't know, call this function here and feed it the 3 arguments. So 3, comma, a, comma, b, comma, c. I guess it will consume a bit of more stack. So in this case, we managed to actually run out of stack space inside this function call, which is also something that can happen. We could still call ourselves almost the same amount of time. So as said, it depends on the complexity, but we apparently have not increased the complexity here enough for this to matter. But generally, this is how this type of bugs happens. And when creating a thread, if you know that you will have a huge amount of recursion of functions that needs a lot of stack space, then you could tell at the thread creation time, we will be taking a look into creating threads in one of the later lectures, of course. So then you can just tell it to, for example, use twice the default size. Then we could have called ourselves here not 9,000 times, but 20,000 times, for example. But it still is limited, and it is a hard limit. You cannot change it once the thread has been created. Hypothetically, one could think of a mechanism that might implement a way of changing it, but the problem is that for this to work, you need to have the address space. So the memory, when you create a thread, the whole memory for the stack, it will not be committed instantly. So in the moment you create the thread, the memory will not yet be used, but at least the address space for the memory will be already reserved. And then, of course, when you create other things in memory, the next address in the address space might already been used for something. So thus, you not always have the liberty to extend the amount of memory that you have already committed or rather reserved to the stack. And this brings us to how this memory management mechanism on modern systems generally works. So every process in your system will get an entire address space to itself. So starting at 0 up to all f's, and in each of those address spaces of every program that runs on your system, you can map in different physical address ranges. So let's say at address 0 1 0x1 0 0. One program can have something and another program can have at the exact same address something completely different. And this is done using so-called page tables. So these are memory structures in memory which the CPU uses to describe those memory mappings, and those memory mappings are done in the granularity of one page. On most modern systems, one page is 4 kilobyte. Also on very non-modern systems, this size is since the last century used basically. Some very modern systems like some ARM chips might by default use a different page size, like for example 16 kilobyte. And in principle, this value doesn't is not necessarily hard coded on the hardware level, but it is something that your operating system defines when it initializes the memory management mechanism. So you cannot have like one program using 4K page tables while another program uses 16K page tables, but you can have a situation where when your operating system initializes the memory management units in the CPU, that you can define whether you want everything to operate with 4K page tables or if you want everything to operate with 16K page tables. Generally, nowadays, since people use a lot of memory, larger page tables means less memory management overhead. The downside is that some old applications may just assume a 4K page size, and thus, if you would use a different page size, those applications might fail. So, usually on systems where compatibility with old software is relevant, everything just still uses a 4K page tables. One popular example that is different is Apple Silicon. They since they switched to ARM and all the software needed to be compiled anyways, they just say, okay, at this opportunity we'll just do 16K page tables. And if I recall correctly, their memory management implementation actually cannot even switch back to just using 4K, which was one of the things that made Asahi Linux for Mac a bit more challenging, because there you needed to ensure everything works correctly with 16K page tables. So you have this individual memory pages, 4K usually each in size, and the operating system, through the use of this memory management unit inside the CPU, can then really assign individual pages from the physical RAM that you have to those virtual address spaces for every application wherever it finds it useful to do it for that application. So in case, for example, of the stack space, the operating system, when you create a thread, will reserve the address range for the entire stack, but only allocate one or two pages, and then when your application calls a function, which calls a function, and which calls a function, and the function will try to write to the next page which has not yet been allocated, this will cause a memory fault. But since all the exceptions and faults are always caught by the operating system before they are passed to the application, the operating system will just see, aha, this is a fault related to the memory not being yet allocated, and it's an address which lies within the boundary of the stack. So I will just pick some random empty page from the physical memory, set it in the page tables for this process to be mapped to this address where this thread tried to access, and then I will instruct the CPU to retry the last tried operation. So then basically the last opcode that caused a exception, the CPU will just jump again to it, and now since the page table has been allocated, the operation will succeed and your program will keep working. And then as soon as you are a bit deeper in your call hierarchy, this will repeat again, a new page will be mapped in. Of course, in practical, the operating system might think, oh, I needed already to map in like 3 pages in short time, let's just map in 10 pages. So I won't be bothered anymore so often. So this is of course an optimization which many systems might use, that they will kind of try to intelligently decide how many more pages to give whenever such a page fault occurs. And another mechanism that here is very worth mentioning is that since we can have uh, committed memory address ranges for which we might not have yet physical memory actually uh, mapped into those ranges. This mechanism can be used to implement virtual memory. So one thing that I'm sure you notice on Windows is often that sometimes it shows that there is more memory used than there is physical memory on your system available. And this mechanism was in principle already available in the very old Windows 3.11 and other very basic Windows versions, and it uses this exact mechanism. So um, when the operating system notices that you are reaching the actual physical limit of how much memory you have, it will look which parts of memory which are currently in use by applications have not been used recently. It will just then take those pages, write them to disk, unmap them from those processes, and the physical memory in the system will be marked as available again, as free. And then if one of the applications does something and runs into such a page which has been paged out, as the terminology goes, then this will cause an exception. The CPU will see, aha, it's a page fault. So have I paged this page out? Yes, I did. So let's just find some empty page in the physical memory, copy those page from the disk back to RAM, and then map this page into the address space of the process, and then let's tell the process to continue as if nothing would have happened. And then the process continues and everything works fine. The only major, of course, downside is that those operations are extremely slow. So if you run out of memory and you have a lot of programs that are actually doing something and not just sitting around doing nothing, then everything will slow down to a crawl because the operating system will be busy most of the time by putting things into memory and out of memory and back into memory and back out of memory and so on and so on. So this much generally to the modern virtual memory mechanisms. There are a few aspects of the memory layout that are still worth mentioning. One is that the page which starts at the address 0 is defined, not in hardware, but defined like on a level of just operating system design as invalid. So the operating system will never allocate the 0 page to an application. At least not on the modern systems. Older systems like that needed MS-DOS compatibility, in fact, did this because there are things located there which the DOS programs might want to access. But since usually the value 0 for pointers is used as a stand-in for an invalid or not yet set value, it is of a great practical benefit to just never actually map the 0th page in modern systems, because then if something tries as a null address, then it will just create a nice crash, and that's it, instead of actually finding some valid memory at address 0. And another such memory space layout design is that you need, of course, your memory for your application, but your operating system also needs some memory for itself. And the way often data are exchanged between those systems is that you would not want to need inside of the kernel to remap everything each time. You would like, when you are inside of a operating system kernel call, to be able to directly access all the kernel memory and all the processes private memory as well. And the way this is done is simply by hard partitioning the memory range, the available memory space, in user space memory and kernel space memory. The user space memory will be everything after the 0th page up to usually the middle of the address range, address space available. And then the kernel will pick its own addresses, usually starting at the very top of the address space. And since this is a hard limit, effectively an application will never be able to use more than half of the address space, even if more physical RAM would be available in the system. On 64-bit systems, this is still a rather academical limitation. You won't be able to afford so much RAM to run into this problem. but on 32-bit systems it was quite common that you might have a server with 8 gigs of RAM, but your address space was only 4 gigabytes. So what happened there was, first of all, the operating system kernel could only use 2 gigs for itself. Any application could use only 2 gigs, but you could have like 3 or 4 applications, each using 2 gigs of physically available RAM. So this is something that is worth knowing that such a mechanism existed, and the old versions of Windows had a switch that allowed you to change the partitioning. So instead of having the cut exactly in the middle, you could also say there are 3 gigs for the applications and only 1 gig for the operating system. Um, of course, there are practical limitations to this. You might want to allow the operating system to use more memory, but then um, well, it won't be able to, so you would run into other sort of out-of-memory errors. And I said on modern 64-bit systems, you won't be able to afford enough memory anytime soon to have more physical memory than you have room in your address space. That brings me to another interesting aspect, is that on a 32-bit system you might find yourself in a situation where you have kind of enough memory free, but then if you try to use this memory, you will get a not enough memory error. Because when you try to use memory normally, as we will try shortly ourselves, you are basically requesting a consecutive amount of memory from the operating system. And if you have a very small address space, it's possible that there is enough unused space in total, but there is not enough unused space in one consecutive range for what you want to do, and then you would also get a out of memory exception. Um, yeah, so that's about this. And of course, as said, with a 64-bit address range, the address range is so vast that you realistically will not run into it. You will only be limited by the physically available memory. So let's start doing something. So we had the stack memory, and the other type of memory, as I said, you can request memory from the operating system, is called heap. With the stack, the idea is that when you are kind of allocating memory on the stack, you're just decreasing the stack pointer more and more. And then if you want to kind of return this memory so that it can be again used by something else, you have to do it in the same order you did before. So you cannot like put back something on the stack if things that come after it hasn't been yet put back. So to say, as the name stack suggests, you need to keep to the same order, like, or rather the reverse order. So you take elements 1, 2, 3, 4, and then you need to return 4, 3, 2, 1. You cannot return them in random order. With the heap, it is different. The heap memory is something that is being allocated for your process, also on process creation, at least some amount of it, and then you can request more and more and more, and the more you request, the more blocks for the heap will be allocated by the operating system. So it's a multi-level memory allocation mechanism. We will be taking a look into this in more detail soon. But the important thing is that you can request stuff from your from the heap memory, and then you can return it in any order you want. There is no enforcement that you need to do it in a particular order. So let's do it. So as you know, if we have memory, we need some pointer. So let's go with some void pointer. My memory 1, and we use here there are a few functions which can be used to allocate memory, and the most common of them is malloc. It's just short for memory alloc. And we just specify the size in bytes, how much memory we want. This function, as here, is not directly a operating system call, but it's a part of the C framework. So it's a function that will call some other functions that will only at some point ask the operating system to give us more memory. And an important aspect is that, as you might already suspect, since the operating system works with memory pages, when we ask the operating system for memory, it can only serve our request with the granularity of page. So we can ask for 1 page, we can ask for 10 pages, we can ask for however many pages we might think we might want. But we cannot ask the operating system just, hey, give me 5 bytes or give me 126 bytes. It could only give you 4K, 8K, 16K, etc. So this would of course be quite inefficient if whenever we want some small amount of memory, we would just ask system, hey, give me 4K. I only need 100, but give me 4K. Uh, well, if it would be money, it would be nice. But with memory, that would be, as with money, extremely wasteful. So our application would use a huge amount of memory, even though most of the memory would be empty. So usually the way this is handled is that we have in our C runtime such a function like malloc, which will maintain together with its other helper functions. So malloc is not the only function that is part of this mechanism. There's a whole set of functions which we'll be using shortly. It will just, once you call it, it will say to the operating system, hey, give me, I don't know, 100K. That's a good amount to start, and then it has 100 kilobyte of memory, and then if your code requests 100 bytes, then it has a range. It keeps own bookkeeping, so which parts of this range are already used and which are not, and then it will give you 100 bytes or 4 bytes or however many bytes you wanted. And then if you ask for more, it will then give you more and more until it kind of gives you all the 100K that you have requested from the operating system. At which point, if you want more, it will just without any interruption just ask the operating system, hey, give me another 10K or however many, or a megabyte or 2 megabytes, whatever. And then it will then give you some of that memory, and then you can ask it again for more and more, and then it will give you more and more until at some point you run into the same situation then in which it will then again ask the operating system for a bigger amount. And while you're of course doing it, you can return memory to this memory manager that runs inside your application. And the memory that has been returned to it can then again be given out if you ask for it. So it's not like that it's wasted or something. One thing, of course, that can happen is that you will ask for a lot of memory and then keep like a chunk here, a chunk there, a chunk somewhere, and a chunk somewhere else. And ideally, of course, you would want your application to allocate some memory, and when it is done using most of the memory, you would want your memory manager to be able to return this memory to the operating system. Basically meaning tell the operating system, hey, the memory I have in the range from here and here and from there to there, I don't need it anymore. You can unmap it and use it for something else. But you might find yourself in a situation where in most of the blocks there is at least a few bytes which are still used by something, and then the whole memory cannot be returned. So if you, in some scenarios, it might be beneficial to create some additional memory management mechanisms of your own, but this is something for later. For now, we will just go with this built-in heap manager that is part of the C runtime, and yeah, and that's it. So here with this 3 function calls, we have allocated 3 memory blocks. We can put a breakpoint and take a look on the memory we have got. So memory, we had here one memory viewer, zack. As you see, it's all pre-filled with CD, which indicates that it is not yet been well filled with something. If you would use a release build of the application, it would not pre-fill the memory, because pre-filling it is again kind of wasteful. But for the debug purpose, it is also very useful. So we have all this memory. One thing, of course, that might happen is that if we want too much memory, at some point the operating system will say, well, sorry, I'm out of memory. And then this function will return a null. So if this is 0, then we have an error, return -1, for example. And of course, we should do the same check for all the other memories we have requested before. So of course the error can happen with any of them. So whenever you are requesting memory, you need to explicitly check whether you have actually gotten it, because you might have not. With the stack, it's different. As you have seen, when we run out of the stack, the thing just crashes. Here we don't have a crash, it's a graceful error, and we just then know we need to somehow return something that we would interpret as error out of memory or something. Right, and once we have this memory, we can do something with it. So, for example, we could open one of our other projects to copy something. useful. So for example, often when you are requesting memory, you want a bigger block, and if you have a bigger block, you probably want to put something bigger into it. So usually it is typical that when you have some memory, I mean, you could of course use it as, for example, an array of integers or something, but you could also use it as such a thing. We could just add an array, char array 100. So we have some structure, and then we want it to be allocated on the heap, not on the stack. So we would have our pointer, my ptr, and then we have our malloc, and then we tell it how big it is, size of, and the thing complains because of course the type is not right, so we need to cast. And then we can work with our structure, and we can pass it to a function. We can, so for example, a common use case is that you have a function which would have a structure asterisk as a return type. The function internally will do something, and then it will allocate some memory, and then it will return to you the pointer to that memory. One thing that one needs to keep track of is how the memory was allocated. So if you have a function that returns something allocated with malloc, then if you want to return the memory, you need to use the right function. So in case of malloc, it's just a free function, which just frees a memory block. So we can free it here. 1, 2, 3. And then of course we want, let's move this maybe further down. Here just do something. Yes. And of course the important thing is you can return it in any order. So let's just make the order randomly. So let's say 1, 3, 2. This is a nice random order. Yeah, and here we continue. And if you would add other or use other memory allocation mechanisms, ones which are not necessarily compatible, then you would kind of need to track which free or which function that does freeing to call. So a typical situation where you can run into such a scenario is if you are loading libraries, and the library will have some internal memory management, and then it returns to you a address. Then you might need to call a library specific memory free function instead of the generic free. This, for example, happens also with some of Windows' own APIs. They have in the past used a bit more various memory allocations. Nowadays this is a bit more unified, but for compatibility reasons you are provided with the right free functions. In practical cases you might be successful with just using the normal free, but often the APIs will be specified that if you get some memory from some API, then you need to use this free memory function to release this memory correctly. Yeah. So, any questions so far? Okay, if there are no questions, then let's continue. Right, so we have memory. We have allocated it. Similarly to our Stack Overflow, if we call this too often, we might run out of memory. So let's try it out. Let's create a function. Right, my memory leak. And this is a very common type of errors, but unlike the other errors that I demonstrated to you in the past, this one is quite safe. Safe in the sense that you cannot use it to exploit the system. You can just, the application will just crash, but it's not something that would give you an angle how to take control over someone else's application. So we have something, we do something, and then we go get to free, and then we just return. No, return. Let's make this an int. Maybe we want to return something. But the important thing is because for example, this is something that might be quite common, that you provide some arguments and then you want to internally make some longer computation for which you need to allocate some memory, and then you have your return value, which you just return as an integer, and then you just, as said here, you forgot to call free on the memory that you used for your scratch pad. So of course, if we just call this function once, nothing bad will happen. We just call it, and then the application just finishes fine, because this amount of memory, if we leak it, it doesn't matter. The problem starts to be bigger if we have, for example, a loop that runs forever. And I mean, realistically, of course, not that runs forever, but that runs for often enough. We could, of course, also have here some counter. And e equals 0, e plus plus, and e is less than int max. So that int max is like 2 billion, so I think we will run out of memory before that happens. We might also want to monitor our memory usage. We actually already are kind of on the limit. This virtual machine has only 8 gigs allocated to it, so it is not particularly well equipped. Let's run it, and then we'll of course see that this here goes up, and kind of we don't even get a crash because we are not actually doing anything. If we would be doing something, then we would crash at some point, because at some point here the thing will just start returning 0. So we can put a breakpoint, and actually it gave us some memory. Yeah. We are now hammering the page file. This here is increasing, so we kind of still get memory since we don't use the other memory. You see here the page file is growing and growing. At some point Windows will say it's enough, I hope. But since we are not using the memory anymore, it's kind of somewhat safe. Okay, at 32 gigs the operating system decided that is enough. It won't allocate more memory, and here we will it still works, but at some point it will stop working. It might also be somewhat like random, that sometimes it works, sometimes it doesn't. Oh, did we just, well, the whole thing almost froze. I think we should just kill it before we kill our operating system. Also, you might notice that now the total amount of used memory is much smaller, because a lot of things that were kept resident in memory have been paged out and are now on disk. And once we start an application that needs it, those things will be returned to memory from disk. And on Windows, if you are interested, the page file is called page file here, and this is where all the data goes if your RAM is full. And there is some limit. As you see here, it is shrinking. So it started out, it was at some point like 32 gigs, but now it's already 4, which is about probably as much as there is still of needed stuff. So at this point, kind of having a memory leak, if you never use this memory, it will just get paged out and kind of forgotten. You can afford a large leak before you get a real problem. But of course, this is not something that can in any way be considered good behavior, so you should always ensure that whatever memory you are using, you are freeing again. The nice thing, of course, is that as soon as your application will crash, and at some point it will, the operating system will just free all the memory that that application has allocated. So the operating system tracks this, and once your application gets terminated, the memory will be freed. So it's only a problem as long as your application is still up and running, at least for other applications. Right, so that was much to our memory leak. Yeah. Do we need to demonstrate anything else? I don't think so. So this is already kind of good enough. As said, this malloc is something that does quite a lot internally, so we can also kind of directly request memory from the operating system. Virtual alloc, and it's called virtual alloc because it is allocating memory in the virtual address space. So void stern my raw PTR, and then the thing actually gives us even the opportunity to tell it at which address we would want this memory to be allocated. But we can say null, which will just tell it, just pick an address for us, and then we have to say how much we want. So let's say 0x100, this is 4K, this is one page, and then we can specify allocation types. So the memory, when it's being allocated, you can tell it various properties that it should have. But for our use case, let's see, what do we want? Mem, mem commit and mem reserve. We just want it to be ready to use, and then we can specify for the memory pages that we will now get from the operating system the page protection. So what is allowed to be done with this memory, and the page protection generally will allow you to specify whether it is readable, writable, or executable. And as I think I already mentioned at some point, um, ideally you would never want to have memory writable and executable at the same time, because this is risky. Because if someone finds a way to get something into somehow to override this range, then it will overwrite your code, and as soon as you jump to this code, you will execute then the attacker's code. So you would want, for example, in our case, let's go with page read write, and oops, it's again page read write, and that's it. And of course, there would be like page read write execute somewhere. I execute read write. But ideally, you would want only to execute read, which allows you to call the code, to read the code, but it doesn't allow you to change the code. If you try to change it, the application will, well, at this point, the crash will occur. And this can, in principle, be also changed. So there is, was it a virtual protect, where you can specify an address and a size. The size again just is used to determine how many pages this applies to, and then you can specify some new protection, like for example page just execute read, execute read, and then you get in fact an argument where you can get the old protection state for the memory range. So often, if you would want to modify some executable code, you would start the other way around. You would start with some page that is execute read. You would switch it to read write, or maybe even read write execute if you don't want, maybe things are using it, you don't want it to crash. Then you would do your modification, and then you would use the value that you got before to restore the old protection that was set before. And of course, once you are done with the usage here, you can also use virtual free to free the memory, and then you. But as you see here, virtual free wants not only the pointer, but it also wants the size. So at this point, you need to track not just the pointer that you've allocated, but also how many bytes you have allocated. And I think it also wants some flags. Let's go with 0. The things that are built into the C runtime, like malloc and free, are kind of much more convenient, because while of course for malloc you need to tell it how much you want to malloc, you don't need to trace how much you actually have malloced. You can just malloc more than you need, then do something with it, and then you just need to have the pointer and tell it free. And of course you might wonder, how does this work? Right, so let's there was a question in the chat, can we somehow free use the memory if we haven't explicitly defined some space with malloc? So you can use virtual free to free something. So we could just virtual free the address of main, and then the application would crash. So yes, we can free it, but we can only kind of free it on the level of the operating system. And then we can free any memory at any address that belongs to our process. Okay, but let's return here to this malloc and this free mechanism. So the way it works, that when freeing here from malloc, it does not require any size, is that because of the internal bookkeeping that malloc and other memory allocation mechanisms use, it is detailed enough that if you give it any memory address, so even if you would kind of try to free not my memory but my memory plus 5, it would still find the range that it gave up, the entire range, the correct range and then free the entire range. So this is not necessarily documented behavior, so you should not rely on free of a memory address working for free of a memory address plus offset. But in practice, at least with some implementations of free, that works. But as I said, you should not use it because it's not a documented behavior. Documented behavior really just is that you have allocated something, and then if you pass this address, it is able to resolve where the right allocation entry, the right size, and then free it. And how this works internally is up to the developers of the C runtime. There are a few ways how this can be done. One method is, for example, that you keep a list or a sorted map of all the addresses that you have given out, and then in this map you can always look up very efficiently by address the right element or the element closest to the right element. And then if you look it up, you can check, okay, so this many bytes have been allocated in total, and then you can accordingly update your memory allocation. Such an approach is quite error proof, because um, if you do something with your application with the memory that you got by malloc, you cannot really break it. Of course, if you just start overwriting random addresses in your application's address space, then you might destroy those management structures. But given the size of a 64-bit address space, you would have to be exceedingly lucky to hit something randomly. Of course, if you try to do it on purpose, there is a process environment descriptor block which contains the exact address of your default application heap, and then you can go on it and destroy it. So generally there is always a differentiation whether whether things are safe against just errors and bugs, and whether they are safe against malicious tampering. And within your own application you don't have any safeguards against malicious tampering, so you can only have systems which are safeguarded against random issues. And for example, one of those mechanisms would be that if you ask some memory with malloc, then you will get a block. But if someone else asks for some memory, they will never get like the block just directly next to your block. They will just get something which is slightly further away. So that if you overdo your, for example, if this would be some arrays, and you get a very common error is that you either have like, so usually arrays are like indexed with 0, but you might forget it and start the index with 1, and then you will also try to, so you will kind of not use the first element, but you would use like one element after the last element, which does not actually exist, that was not allocated. Of course, if your elements are very large in size, then the heap allocator might not, of course, it will not know it, but for example, it can assume that it will always keep at least 8 bytes additional memory, which would be for at least the built-in types enough for such an error to just hit then unused memory. And another thing the debug heap on Windows at least does is that to this memory space that is surrounding the memory block you have requested, it adds a special pattern. And then if you make free, it checks whether this pattern is still intact, and if it is not, it will throw an exception on your free operation, indicating to you that whatever you did with this memory, you exceeded the bounds of it. So this is a very useful debug mechanism. In release applications, of course, it's not present, but in a debug application like we have here, it is, and it's very helpful to find such memory corruption errors. So generally, the way this strategies for memory allocation are implemented is that the system tries to catch errors in debug builds, while in the release builds it tries to make the errors have as little to no impact. So like just giving you more memory, so that if you have an error, that you just trash some unused amount of memory and so on. While on the release, on the debug build, it will behave differently. This is well, one strategy how this memory management can be done. Another way how you could manage memory would be that you instead of having some memory management structure somewhere else, at least with regard to the size parameter, that you kind of create a bit larger block. You write some metadata at the beginning of the block, and then you give out the block as a, well, you give out the address somewhere within the block to the caller, and when then free is called, you get the address. You know your own information starts at offset minus, let's say, minus 16 from the address, and then there you just look up for your stuff. And such an approach is of course much more error prone, because if you would have some error with your indices and go to an address before your the address that you the starting address that you got, that then you would start and overwriting those memory management regions. That said, such strategy where you are kind of just hiding away a few of extra bytes before the memory you give out is quite common with self-made memory allocators, because it's a very convenient and easy way. Maintaining additional tables is also less efficient, because then you, on every free, you need to actually make a full lookup, which will take time. And the general main use case to create your own memory allocation mechanisms is that you want it to be actually very fast and very efficient. And usually you will trade in other things, like you will trade in fault tolerance, or you will trade in the liberty to select the size. So this is a very common type of a memory allocator, where you just will always allocate blocks of a fixed size and always only give out blocks of this size. And if you are doing some math with some matrices and you know the size of the matrices, then it's very convenient to just use such a approach with a fixed size. But of course, it is then only application specific, like task specific. You cannot reasonably use this for some general purpose. While the memory allocator that comes with the C runtime in Windows and Linux and other operating systems is of course designed to be as flexible and as generic as possible. And I see we are running out of time, so before we do that, I will just show you one more thing you can do with memory. There is a function called realloc, and what it basically does is you can give it a memory range and give it a new size, let's say 2000 bytes, and it will return you either a new or the same memory address, which contains the data from your old block, but where now the block is much bigger. And the idea is here that if you just allocated some memory and then you decide, oh, you need more, and then you can ask the heap manager to do this reallocation for you. And this thing, since it does the memory management of the bookkeeping, it can look up, is there actually free address space or already allocated memory but not yet given out after the end of the currently allocated and assigned memory range. And if there is, then it can just give you more memory from the already allocated blocks, or allocate new memory at these addresses, and then it can skip the copy operation. Then you basically will get as a return for memory the same address, but now you know that there is much more room after this address. And of course, if this is not the case, if it sees, oh, the next block I have already given this out to memory 2, for example, then it will just allocate a whole new larger block, copy the things over, and then give you the new address out. So the general idea of this realloc function is that it can be much more efficient if you are lucky. And generally, if you have some operation where you grow an array and then grow it some more and then grow it even more, then it is quite often the case that you will be lucky and be able to get more memory without having to reallocate actual memory with the operating system. And this is okay, we are really out of time, but just to summarize it. And generally, one thing that you really want to avoid is a lot of memory allocation operations through the operating system. Those are very slow, because they are related to a lot of internal bookkeeping that the kernel has to do. So ideally, what you want is you want to get as much memory as you will need from the operating system at the beginning, and then just work with it. And once you are done, you are done. And generally here, this malloc and realloc and other functions are faster than just directly calling virtual alloc. I mean, they are only then faster if this memory has already been allocated and they have it to give out. so some calls will be slower because then it will internally do a virtual alloc and grab a next big chunk for you to play with. But most of the calls will be much faster because it will be then only giving out memory from this block. But as said, because it still is related with some amount of overhead and internal bookkeeping, you will realistically, ideally try to also avoid, or rather not avoid, but try to minimize how often you call malloc. So for example, if you would have a loop where you want to do something with a memory block, and it's always the same memory block, you would not have like inside of your loop a malloc do something free, next iteration malloc do something free. You would just malloc before the loop, do something, then do something more, then do something again with each time the same memory, just overwriting it, and then after the loop you would free it. Or as said, in extreme cases you might even want to write an own memory allocator, which you then feed some blocks either from malloc or from virtual alloc. But then where internally you would have some own simplified bookkeeping to make uh, the operations with this memory more efficient. And one thing that you can do as a kind of trick, at least on Windows, is you can create more than one application heap. So this malloc and free, these are basically wrapper functions for one heap that was created for your application by the C runtime on process creation. But Windows in fact allows you to create multiple independent heaps. So handle, and then the nice, oops, that's a typo, heap, heap create. We don't care for these options, we just pass zeros everywhere. And then you can, right, and if you want of course the application heap, the one that was created for you, you can also directly address it like this, get process heap, that just gives you the pointer to the one heap that already exists for you. You can use it instead. And then once you have the heap, instead of malloc you would use heap alloc. Then you pass the heap to it, and then of course some flags. Here we can of course let's go with heap 0 memory, so that we want it to be filled with zeros, and we specify a size. And then of course we need to catch this void, oops, void my block, yeah, and then you do something with it. And when you are done, then you need to free it, and then you do it of course with heap free. And now that the important thing, you need to know from which heap you have allocated. You need to provide the heap it belongs to, then you need to provide some flags. Let's just go with 0, and then you need to provide the memory block. If you provide the wrong heap, the thing should crash, or should just throw an exception, or maybe it will just do nothing, but it will definitely not work. I think it will just return false, probably. But one could review the documentation how it handles it. But given that it has an internal bookkeeping in the heap, if you provide a valid heap but not the right one, it would see that the block doesn't belong to it, so it probably would, without a crash, just return a false indicating an error. The useful use case for this trick with creating a new heap is that instead of freeing every single block individually, you could have something where you're just allocating a lot of blocks from the heap, and when you're done with it, you just call heap destroy, heap destroy, oops, with the heap, and then instead of doing instead of doing bookkeeping internally and stuff like that, the whole memory that was allocated for the heap will be just returned to the operating system very efficiently. So this is quite an middle ground, let's say, between doing a full own custom memory management and using the application heap, risking that a lot of memory might stack be stuck in a way that you cannot free it, because inside the whole page some bytes are still used. So here, if you use this method, you can really ensure that you can get rid of it, because if you do the heap destroy, then you are really freeing all the pages. Of course, at this point, it is up to you to ensure that you have not returned somewhere from your functions an address to something that was allocated here inside and then still will be needed once you destroy your temporary heap. Okay, but this is it. So that much about memory management. I would like to remind you that the next lecture next week will start at 10 o'clock in the morning instead of 3 in the afternoon. This is just a one-time exception, so I hope you can make it. If you cannot, no problem, you can watch the recording later on. But of course, I would be happy if as many of you as can accommodate it would, of course, appear next week to the a bit sooner lecture. If you have any questions, you can email me at any time. And that's that. So let's stop the record.